Welcome to today's lecture on seismic static analysis. In this session, we'll explore the horizontal distribution of floor shear, a critical factor in understanding how seismic forces impact buildings. When an earthquake occurs, forces aren't applied randomly. They are systematically distributed across the floors. Today, we'll break down the fundamental principles behind this distribution and examine a few examples to apply these principles. Let's dive in. Before we delve into horizontal distribution, let's take a moment to briefly review what we've discussed thus far. In our previous lectures, we concentrated on resolving the base shear. Once that was established, we examined how those forces are distributed, utilizing two primary approaches: vertical and horizontal distribution. As you may recall, we already covered vertical distribution in our last session. Today, our focus will be exclusively on the horizontal aspect. With that foundation in place, let's proceed. Now, here's a quick overview of what we're going to cover today. We'll start with the distribution principle. Then, we'll work through example 1, which deals with a concentric horizontal distribution. Next up is example 2, where we'll examine a system with eccentricity, compute the center of rigidity, and see how force distribution works in that scenario. We'll also dive into the derivation of relative stiffness, and we'll cover the derivation of torsion. Finally, we'll wrap up with example 3, which looks at horizontal distribution with eccentricity, including computing the center of gravity, determining torsion, and distributing force. Let's take a closer look at why the arrangement and location of lateral force-resisting elements are so critical. The ability of a building to resist lateral loads during an earthquake largely depends on these elements. Their configuration not only supports the vertical loads, but also plays a major role in how the horizontal forces are spread across the structure. Moving forward, it's important to note that every floor carries its own share of shear loads. However, when the force is applied away from the center of rigidity, in other words, when we have an eccentrically loaded system, it creates torsion in addition to shear. This means that both effects must be considered in our analysis, as shown on these slides. In these slides, you can see that the total shear force isn't absorbed by just one element. Instead, the force is distributed among all of the lateral resisting elements. This distribution, based on the stiffness of each element, ensures that the load is balanced across the structure. Here we highlight an important point. Every lateral force-resisting element not only carries shear, but also experiences the effects of torsion. This combined action is what we need to account for when designing and analyzing structures under seismic loading. Let's dive into our first example. Example 1 introduces a basic scenario of concentric horizontal distribution. This example will help clarify the fundamental principle of how shear is divided among the elements when the force is applied through the center of rigidity. Take a look at this sample problem. The floor level, with the floor plan as shown, has a shear force of 50 kilonewtons passing through the center of rigidity. If the stiffness values are provided for each resisting element, what will be the horizontal distribution for each element? We'll use this problem to illustrate how we calculate the distribution based solely on shear. The force in each element, which we'll denote as F, is computed by taking a weighted percentage of the stiffness of that element relative to the total stiffness of all elements on the floor. Now, the formula we're using is straightforward. It takes the shear force and distributes it according to each element's stiffness ratio. This formula is the backbone of our analysis in this part of the lecture. Let's look at a specific case, the middle column. For this column, the force is calculated by multiplying the total shear force, 50 kilonewtons, by the stiffness of the middle column, then dividing by the sum of the stiffness of all elements. This gives us the proportion of the shear force that the middle column will carry. Similarly, for the other columns, we apply the same process. Each element's force is computed based on its stiffness relative to the entire system. This method ensures that every column or wall takes its appropriate share of the load. Now let's move on to example 2. This one is a bit more intricate because it deals with an eccentrically loaded system. In this scenario, the system is loaded with both shear and torsion. The problem statement says, determine the distribution of force of the structure shown. Consider the torsion. In this example, we first determine the center of rigidity, denoted as CXR and CYR. By assigning a coordinate system and calculating the distances of each element from this center, we set the stage for analyzing both the shear and torsional effects. This is a critical step in ensuring our force distribution is accurate and reflective of the actual behavior of the structure. It would also be convenient to label each element with letters for easier identification. Now, let's talk about how we compute the center of rigidity, both for the X and Y axes. Here's how it works. We start with our chosen origin, the bottom left corner of the floor plan. For each lateral force-resisting element, we multiply its stiffness by its distance from this origin. Then, we add up all those products. Finally, we divide the total by the sum of the stiffnesses of all the elements. This calculation gives us the coordinates CXR and CYR, which represent the balance point, where the lateral forces are most effectively resisted. Essentially, it tells us how the overall stiffness of the structure is distributed in both directions. Once we've determined the center of rigidity, we shift our coordinate origin. For each element, subtract the center of rigidity's coordinates from the element's coordinates to obtain the distances x, r, and y, r, which represent how far each element is from the center of rigidity. Note that the formulas for xrr and yr are oriented in opposite directions, so the xrr values may appear reversed relative to the standard coordinate system. This setup is intentional and will be advantageous for later calculations. Alright, let's talk about how torsion changes the game here. Unlike example 1, where we only split shear forces based on stiffness, now we're dealing with two effects: direct shear and torsion. The total force on an element becomes a combination of both. Let's break it down. The torsional force formula, Ft, is T times K times R divided by J. Here, T is the torsional moment, force times eccentricity, and K is the element's stiffness. R is the distance of the element from the center of rigidity, and J is the polar second moment of stiffness, calculated by summing up K times R squared for all elements in both X and Y directions. Think of J as the system's total resistance to twisting. The stiffer or farther an element is, the more rotational load it carries. Now, notice the plus or minus sign in the formula. That's critical. Torsion can amplify or reduce the direct shear force on an element, depending on its position relative to the center. If it's on the side where the twist pushes, forces add up. If it's on the opposite side, they cancel out. This is just like eccentrically loaded bolted connections in steel design, where bolts take both shear and prying forces. Same idea. But here's the catch. Direction matters. Since we're working in X and Y coordinates, forces have components in both directions. You'll need to calculate Fx and Fy separately, paying close attention to positive and negative distances from the center. A quick sketch of the forces helps visualize which direction they act. Navigating sign conventions is a common challenge in these calculations. To streamline this process, we will systematically integrate directional signs directly into our analytical framework. Here's the methodology. First, we align shear direction with the defined coordinate system. Forces acting in the positive X or Y directions are assigned positive values. For torsion, a clockwise rotation, when viewed in plan, is designated as positive. By embedding these conventions into our formulas, we ensure consistency. For instance, when computing distances from the center of rigidity, xr, yr, the algebraic signs inherently reflect an element's position relative to the center. This integration ensures that both shear Fv and torsional Ft forces inherit their directional signs automatically during calculation. This systematic approach eliminates ambiguity. The torsion's clockwise designation, combined with coordinate-aligned shear, guarantees that resultant forces, Fx, Fy, inherently carry correct signs based on their spatial relationship to the center of rigidity. This methodology is analogous to eccentrically loaded bolted connections in steel design, where positional logic dictates load direction. Let's proceed to apply this framework to our examples. Proceeding to the calculation of J, we begin by isolating its components for clarity. Specifically, we first compute half of J, defined as the summation of the product of lateral stiffness in the y direction, ky, and the square of the perpendicular distance of each element from the center of rigidity in the x direction, rx squared. We'll do the same for the other half of J. The summation of the product of lateral stiffness in the x direction, kx, and the square of the perpendicular distance of each element from the center of rigidity in the y direction, ry squared. And then we add the two to get the full value of J. We can now compute for the forces in each element. Let's focus on column A. Based from the assigned direction of the shear and torsion, I am able to identify the direction of the component of the forces applied to column A. Here are the formula for the forces along x and y for column A. We prioritize the calculation of Fy. This begins with determining the total lateral stiffness in the y direction, sum of ky. We then plug the known values of Vy, ky, t, and xr. Notice that the direction of Vy and t are reflected in the formula, and the computed value of xr, including the direction, is also included in the formula to ensure the correct values of Fv and Ft. The result of Fy, with its negative sign, indicated that the applied load on column A along y-axis is directed downwards. We'll compute for Fx using the same approach, but as you can see, the value of Fv along x is 0, since we don't have any shear along x. That leaves torsion as the only contributing factor for Fx component. We'll do the same process for the rest of the elements. Here in the succeeding slides, we compute for the components of forces applied on column B. Computing the rest of the columns, we get the following results. Note that if we add all the values of forces along y and x, the result will be the values of the applied shear force on the system along y and x, respectively. Before we proceed further, it is important to address a critical prerequisite: the computation of stiffness for lateral load-resisting elements. While our analysis thus far has utilized provided stiffness values K for distribution calculations, we have not yet detailed the methodology for deriving these stiffness values. Stiffness, defined as the resistance of an element to deformation under load, depends on material properties, like modulus of elasticity, cross-sectional geometry, and boundary conditions. Stiffness can be in terms of axial, flexure, shear, or torsion, depending on the types of stresses being resisted. Let's have a bit of a review. Under axial stress, the relationship between applied force, P, cross-sectional area, A, modulus of elasticity, E, member length, L, and axial deformation, delta, is governed by Hooke's law, sigma equals E times strain, where stress, sigma, is force per unit area, P over A, and strain, epsilon, is deformation per unit length, delta over L. Rearranging this, we derive P equals A times E over L times delta, isolating force as a function of deformation. This mirrors the linear spring equation P equals K times delta, where stiffness K defines the force required to produce unit deformation. By analogy, the axial stiffness of a member is expressed as K equals A times E over L, directly linking material properties, modulus E, and geometry, area A, length L, to structural resistance. This formulation underpins the axial stiffness used in load distribution analysis. Stiffness formulations are not universal, but instead depend on the structural element's configuration, boundary conditions, and loading type. Take the case of a cantilever beam subjected to lateral loading. Its shear stiffness is governed by flexural rigidity, expressed as K equals 3 times E times I over L cubed. Contrast this with a column in a rigid frame fixed at its base, as shown in the figure. Here, the shear stiffness formula becomes K equals 12 times EI, divided by L cubed. The difference arises from boundary conditions. Fixed supports restrict rotation, increasing stiffness compared to a cantilever. In practical applications, stiffness calculations can often be simplified by leveraging uniformity in material and geometry. For instance, when all lateral load-resisting elements on a floor, such as columns or walls, share the same modulus of elasticity, E, and length, L. These constants appear in both the direct shear, Fv, and torsional, Ft, force formulas. Since E and L are common to all elements, they cancel out when calculating stiffness ratios. This allows us to equate stiffness K directly with the moment of inertia I of the element's cross-section, reducing the problem to comparing relative I values. This simplification, known as relative stiffness, streamlines manual computations while preserving the proportionality required for accurate force distribution. In structural mechanics, the moment of inertia, I, quantifies an element's resistance to rotational deformation. For a rectangular cross-section, such as the figure shown, this is calculated as IA equals 1/12 times C times D cubed. Further, to maintain clarity and precision in our calculations, we adopt a standardized notation system for stiffness in the X and Y directions, grounded in the respective moments of inertia, Ix and Iy, of each structural element. Next to address is the computation of torsion. Torsion arises when a shear force acts at an eccentricity, E, defined as the perpendicular distance between the center of gravity, Cg, where the seismic force is applied, and the center of rigidity, Cr, the structural system's stiffness centroid. This eccentricity generates a torsional moment, T equals V times E, inducing rotational demand on the structure. The inherent geometric offset between Cg and Cr is also known as the natural eccentricity, computed using the same methodology as Xr and Yr. Natural eccentricity yields natural torsion, Tn. This rotational demand arises directly from the system's geometric and stiffness asymmetry, where V represents the applied shear force. The algebraic sign of En dictates the direction of natural torsion. A positive En generates clockwise rotation, while a negative En induces counterclockwise rotation. This sign convention, embedded in the coordinate system, ensures directional consistency for accurate force resolution. Aside from natural torsion, the code also mentioned about additional torsion. The code states that, where diaphragms are not flexible, the mass at each level shall be assumed to be displaced from the calculated center of mass in each direction, a distance equal to 5% of the building dimension. At that level, perpendicular to the direction of the force under consideration. The effect of this displacement on the story shear distribution shall be considered. This can be interpreted as E equals plus or minus 5% of the width of the structure perpendicular to the shear in consideration. The value obtained is also known as the accidental eccentricity. Accidental torsion arises from accidental eccentricity, a code-mandated safety factor accounting for uncertainties in mass distribution and construction tolerances. When combined with natural torsion, these components yield the total design torsion as a result of the total eccentricities in that particular axis. When shear forces act simultaneously along both the x-axis and y-axis, also known as orthogonal application of shear, the total torsional demand on the structure must account for contributions from both directions. That is, T is the sum of the torsion based on both x and y axis, Tx and Ty. Having established the principles of natural and accidental torsion, along with bidirectional shear effects, we will now synthesize this knowledge to tackle example number 3. This exercise integrates all preceding concepts: stiffness distribution, center of rigidity determination, and torsional calculations into a cohesive analysis. The requirement is: determine the horizontal distribution of floor shear of the fourth floor of the structure with lateral force resisting elements, as shown. The provided shear under fourth floor is negative 34.163 kilonewtons. Let us assign an initial origin at the bottom left element. Establish the direction of the coordinate system, and label each elements for easier identification. Since there are too many elements, we organize the information by tabulating the dimensions of elements along x and y, and the center of each element relative to the initially established location of origin. With the element properties tabulated, we can efficiently compute stiffness values in the x and y directions, kx and ky, using a calculator's table functions or spreadsheet-like operations. By organizing inputs into columns, we leverage sequential formulas to automate repetitive calculations. Now, let's calculate the coordinates of the center of rigidity. For the x-coordinate of the center of rigidity, we multiply each element's x location by its stiffness in the y direction. Then, we add up all these products and divide by the total y direction stiffness. For the y-coordinate, we do the reverse. Multiply each element's y location by its stiffness in the x direction, sum those values, and divide by the total x direction stiffness. We can then visualize the location of the center of rigidity in the plan. Now, let's locate the center of gravity, CG, the point where the building's mass effectively concentrates during seismic shaking. To do this, we start by defining the cross-sectional area, A, of each structural element. Next, we sum all individual areas to find the total area of the system. With this total, we calculate weighted coordinates. Multiply each element's x location by its area, A times x, and y location by its area, A times y. Summing these weighted values gives us sigma AX and sigma AY. Finally, divide these sums by the total area to find the CG coordinates. In the same manner, we can also visualize the location of the center of gravity on the plan. With the center of rigidity, CR, and center of gravity, CG, now calculated, we move to determining natural eccentricity, the inherent offset between these 2 points. Next, we compute accidental eccentricities. We first measure the planned dimensions of the structure, edge to edge, in both x and y directions, and apply a 5% factor. Crucially, the sign of accidental eccentricity must align with the natural eccentricity. For example, if ENX is positive, EAX is also applied in the same direction. This ensures conservative design by amplifying torsional effects. Combine both eccentricities to compute total eccentricity, which is then used to solve the total torsion. Let us now solve for XR and XY, the same as what we've been doing with example number 2, but in a tabulated manner, followed by the computation of J. Each ky times x squared and kx times y squared are obtained. Total of this two columns of quantities is the value of J. Now that we have all of the values of V, T, and all other quantities required, we can now proceed and solve for the value of the forces applied in each direction, X and Y. If our calculators are able to sustain long inputs, the calc and colon functionalities are very useful. Shown here is the setup of the calculator input that will simultaneously solve for Fx and Fy for each and every elements. We then solve Fx and Fy. Once the values are obtained, we can now create the illustration of how the forces are applied to each of the elements. In summary, the horizontal distribution of seismic forces hinges on a systematic four-step process. Center of rigidity, CR, center of gravity, CG, eccentricity, and torsion, and finally, force distribution. That's it. Thanks for joining me in exploring the intricacies of horizontal force distribution in seismic design. Thank you for watching, guys, and I'll see you in the next one.